Scientists at the European Centre for Nuclear Research, or CERN, have reignited their cosmic cannon, the Large Hadron Collider. A revolution is about to break out, and by dint of this, the big game of understanding the nature of the cosmos has therefore begun. In light of recent developments and the revived goals of particle physicists, even before undergoing refurbishment, the collider has been producing evidence that the cosmos could be hiding something remarkable. What is the universe's starting point, and as opposed to matter, why does it include antimatter? Join us as we examine the amazing finding that CERN researchers just discovered, which alters everything. Several scientists made international headlines a decade ago when they discovered the Higgs boson, a long-sought particle that gives the rest of the universe its mass. However, what is still lacking? It could be anything, say optimistic scientists. When the super collider was initially turned on in 2010, the entire cosmos was at stake. The Higgs boson was the object of the biggest and most powerful machine ever created. This particle serves as the foundation for the Standard Model, a set of equations that describe every aspect of the subatomic world that scientists have been able to measure. However, the Standard Model is insufficient for addressing some more fundamental questions about the cosmos, including how it came to be, what makes it up, and even why the Higgs particle has mass. Scientists are confident that new findings may provide answers to open-ended questions in science, such as the riddles surrounding dark matter. The fact that the majority of matter in the universe is invisible to humans is a stunning discovery. However, because astronomers have detected the gravitational signs of dark matter, they think that it must exist. A take on dark matter shows that galaxies and galaxy clusters are connected by dark matter, an invisible cosmic structure. We're not entirely sure what it is, but undoubtedly one of science's most interesting mysteries is dark matter. In 2010, we saw the initial activation of the massive collider, and physicists hope that this will lead to some answers. However, other than the Higgs boson, no other new particles or information on the makeup of dark matter were found. Fortunately, there was no impact on the traditional model. The collider was shut down at the end of 2018 for significant maintenance and enhancements. The collider will run again until 2025, at which point it will shut down for an additional 2 years to allow for the installation of other significant upgrades. This round of improvements also includes enhancements to the massive detectors that sit in the 4 locations where the proton beams collide and are examined, as well as the collision debris. Since July, those detectors have been put to the test, as there are many sprays of particles that must be distinguished from one another. Squeezing the proton beams confuses detectors and computers while increasing the possibility of protons colliding at the crossing places. In the meantime, several investigations have highlighted weaknesses in the mainstream model and a more thorough understanding of the universe. These discoveries relate to peculiar behaviors in subatomic particles whose names most of us on the cosmic stage are unaware of. Take the muon, a subatomic particle that briefly gained notoriety last year. What is a muon? Muons, which are 207 times more massive than electrons yet have the same negative electrical charge, are commonly referred to as fat electrons. How muons fit into the whole picture is a mystery. They are created during collider events and by cosmic ray collisions, and only in a few microseconds do they radioactively decay into physical electrons and spectrum neutrinos. Muons spinning in a magnetic field wobbled far more swiftly than the conventional model anticipated, according to 200 scientists from the Fermi National Accelerator Laboratory in Illinois. The world learned about this revelation last year. The parameter called G2, which measures the particle's response to a magnetic field to the 8th decimal place, revealed the discrepancy between experimental results and theoretical predictions. The Standard Model would eventually be destroyed if the existence of the particles could be verified. Scientists have linked the small but considerable deviation to the quantum whisper of a particle that would momentarily develop around the muon and modify its characteristics. For example, the Higgs boson serves as both a powerful telescope and an extremely accurate microscope for studying nature at the lowest scales because it seeks to decay to a lower energy level through a vacuum. It has access to extremely high energy scale physics. Our vacuum is referred to as a false vacuum by physicists. The Higgs field energy potential's peaks and valleys keep our universe in this fictitious vacuum long enough for planets, stars, and galaxies to develop. This false vacuum will eventually degrade since it is intrinsically unstable. This strange quantum tunneling phenomenon, known as quantum energy fluctuations, could be able to break through the energy barrier, allowing the phony vacuum to cross those hills and roll down the slope on the other side. The dissolution of the phony vacuum would spread outward in a wave traveling at the speed of light, destroying everything and replacing it with a real vacuum. Whatever occurs, it won't be for the benefit of the universe. We should be thankful for the existing universe, since only the Higgs field is preventing vacuum decay. Further trailblazing is on the way, as the Hadron Collider's quest to discover physics outside the Standard Model depends on these developments. Despite its great accomplishments, the Standard Model of particle physics is by no means the final word. For example, it does not fit cosmological theories that explain the universe's creation. However, two groups of theorists are still attempting to match their predictions of what G2 should be, as they wait for new data from the Fermilab experiment. One of the 6 kinds of quarks that make up heavier particles like protons and neutrons, the muon, is also involved in another abnormality. The B quark is either the protagonist or maybe the bad guy in this tale. The 2-quark B meson particle has these quarks. However, these quarks appear to violate the Standard Model because of their instability and propensity to dissolve in certain unusual B quark decays. A daisy chain of events may be at play, resulting in the generation of a younger, lighter quark and a pair of light particles known as leptons, which may be electrons or the muons of its fat counterparts, or both. According to the Standard Model, the probability of both electrons and muons occurring in this process is equal. A third, heavier lepton called the tau exists, but it decays too fast to be seen. Despite the lepton universality principle, Dr. Patel and his colleagues have found more electron couples than muon pairings. Similar to the muon's magnetic anomaly, this anomaly suggests the presence of an unidentified influencer, a force particle interfering with the process. Dr. Patel claims that the possibility of a leptoquark, a hypothetical subatomic particle, is one of the most dramatic scenarios. If these facts hold up in future collider runs, the difference between the two sorts of particles that make up the material cosmos may be bridged. If the particle is genuine, protons, neutrons, and light particles like electrons, muons, and neutrinos are made of quarks. Temptingly, there are 6 types of quarks and 6 types of leptons. We are starting this run with more hope that a revolution could be on the horizon, according to Dr. Patel. We are keeping our fingers crossed. Another particle in this bizarre assortment is the W boson, which bears the so-called weak force responsible for radioactive decay. The 10-year endeavor to determine the mass of this particle was announced in May by the Collision Detector at Fermilab, or CDF. Before the building of the Large Hadron Collider, Fermilab's Tevatron collisions, which were the most powerful in the world, yielded around 4 million W bosons, which were all used in this work. Based on the Standard Model and past mass measurements, the W boson should weigh around 80 billion electron volts, the chosen measure of mass energy. In comparison, the Higgs boson weighs around 125 billion electron volts, or about the same as an iodine atom. The most precise measurement to date, the WCDF, however, came in at 80.433 billion, which was more than anticipated. According to the experimenter's 7 sigma estimate, only 1 in 2 trillion times was there a possibility that this discrepancy was a statistical fluke. The W mass boson is correlated with the masses of other particles, notably the notorious Higgs. Therefore, the mainstream model could have another problem if this most recent disagreement persists with further knowledge. The 3 anomalies may all vanish, just as the revolutionaries want. Nevertheless, all 3 point to unidentified particles and forces that conflict with accepted physics, which gives believers hope. As a result, Carl Kramer, a physicist at the University of Wisconsin who takes part in other CERN experiments, hypothesized that the LHC would find a new particle that might account for both the G2 and the W mass. Thus, even though the LHC won't break the laws of space and time, it could enable researchers to shed light on some of the institution's mysteries. Researchers will utilize the LHC to explore the more subtle interactions of the Higgs particles and seek hints of the mysterious dark matter. About 27% of the cosmos is made up of metadata that has never been explicitly observed. Comment below and let us know what you think about this finding.